Hello guys. So, welcome to the last week of this course. In this week we will talk about a small chapter on small oscillations. Small oscillations of course are very useful in applying it to everyday problems, and we will sort of look at the different techniques that I use to solve this problem. Now, I first would like to discuss what is the meaning of the word small is. The small oscillation here means this, that if you take an example of simple pendulum, and we are all very familiar with this example. So, in simple pendulum, let me write down the Lagrangian in terms of the generalized coordinate theta and the length of the pendulum L. This problem of course we have been doing right from the first week. So, the Lagrangian is very simple, it is half ml square theta dot square and plus the or minus the potential energy term there, okay, mgl, and here we identify that the equilibrium point is at theta is equal to 0. So, that is this point where the pendulum remains where it is if you just leave it alone, and you can start oscillation by pulling the pendulum and let go. And if you look at this pendulum problem, if theta is small, and this is the approximation we do all the time, if theta is small, then I look at the potential energy, and potential energy has this 1 minus cos theta, and I can make a Taylor expansion of cos theta about 0. If I do that Taylor expansion, then it will be 1 minus half theta square by 2. So, that 1 would cancel with this, and you get just half mgl theta square, that is for small theta. Now, if theta is small, then potential looks like theta square, and you understand that this Lagrangian is exactly identical to the Lagrangian of a harmonic oscillator, and then the solutions are harmonic. Okay. Now, the question that we would like to ask is this: look at this potential energy diagram there. In the potential energy diagram, so the blue curve here is that of a potential energy of the simple pendulum, and the range of theta is from minus pi to plus pi. And then I have plotted the approximation theta square with this orange curve, and this orange curve of course is valid or matches the original potential curve for some values of theta near 0. And if you look at that part very carefully, then you can see that the two curves here are almost indistinguishable from each other. So, this is what we mean by approximating the potential by a parabolic potential, which is basically potential of the simple harmonic oscillator. But then the question is, small is how small, because as soon as you get away from theta equal to 0, the deviation from the graph begins. It is only matter of how much scale that I would use, or what scale I would use in this graph, that would show me the difference there. Okay. So, for that what I will do is I will look at the motion of this simple pendulum. Let us look at motion where I start the oscillatory motion of the pendulum with initial value of theta, which is 3 pi by 4. Now, 3 pi by 4 means I would be pulling it all the way up to 90 and another. So, 3 pi by 4 I would be letting go of this pendulum from way up there. Okay. And if I do that, what happens to the motion? Now, of course, we are in a era of computational physics. So, we can easily calculate this path of this pendulum or theta as a function of t using computational methods, and here is how the graph looks like. In this graph, there are several parts. First is of course the actual motion. The actual motion is shown by the red curve there. Okay. Now, how good is this, or how close is this to the harmonic approximation that we have done? And in fact, it is not close at all. Look at this green curve, which is harmonic approximation that we had done. Okay. With a harmonic approximation, the red curve and the green curve, they do not look like each other at all. Now, you might say that maybe we have not done a good approximation, and to which I have plotted a simple sine curve with exactly the same period as that of a rate curve. So, actual motion starting from 3 pi by 4 all the way up to minus 3 pi by 4 and so on. This motion is periodic, it has a period. I take a curve which has exactly same period, and that curve is plotted by this blue curve here. And even then you can see that the motion is actually different. The bob pendulum actual motion starts slowly, okay. Theta changes slowly here at the top before it catches up with this sine curve, okay. So, we know that the large angle harmonic approximation will not work. So, what about the small angle? So, I will start with something like 9 degrees, okay, that is pi by 20. With this one, now we are in a good position. Can you see the graph of the actual motion and the harmonic approximation, both are plotted in this graph, and in fact, they are so identical as shown in this graph is that you cannot see the two different lines there, but the second graph is actually hidden underneath this orange graph, okay. And if you look very carefully or expand somewhere, then you will start seeing the difference. But wait, this is basically when you start the motion at t is equal to 0, and I have plotted all the way up to 20 pi. So, that is basically 10 periods. But if I sort of wait and look at this motion for some more time, after several periods, here is what happens. Look at what has happened. Now, the two curves are separate from each other. The motion of the pendulum has drifted from the harmonic approximation, okay. So, this is what is going to happen. The takeaway here is basically the small oscillation does not necessarily mean small amplitudes, but it also means for how long. Once you start the motion, after some time the motion will drift away from the harmonic approximation. So, it is also restricted in time. Now, here I would like to show you one more realistic example. Now, if you search for a branch of paintings or artwork and search for pendulum painting, that is a very interesting idea. You will find several results, you can look at some of those. What they are doing here is basically you have a simple pendulum which is hung, and at the bottom of the pendulum, instead of the bob, I have a cup, and in the cup there is a colored liquid filled, and there is a tiny hole in the cup. So, as the pendulum moves, it sort of drops the ink on the paper which is kept below, and that forms a nice beautiful pattern. Now, of course, the pendulum painting people use this in many different ways. They of course fill the bottle with different colors and so on, but what we want to focus on is this pattern that comes out in the end. Now, this of course is meant for purpose of art, but for us, for physicists, this also means something else. This means I can now actually measure or observe the motion of 3-dimensional pendulum without actually having to record anything. All that I am doing is I just get a pattern here, and I know exactly how pendulum moved in the space there, okay. So, what we decided to do was we did this experiment in our own laboratory in a slightly different way. So, you have a pendulum which is hung there, and in this pendulum near the bob we have fitted one small tiny laser, and as this pendulum moves in the space, it sort of marks a spot on the floor, and then you turn off the lights and do a long exposure photograph, and you get this pattern there, okay. The pattern which would look similar to the pendulum painting pattern that we saw earlier. So, here for this particular case, I would set up a coordinate system on the ground, basically a cylindrical coordinate system. So, you mark x axis, y axis and the z axis being of course vertical, and use cylindrical coordinates. That means, use r, which is square root of x square plus y square, and theta is the angle measured in x y plane from x axis. Now, the Lagrangian we can immediately write down, that it should not be difficult. We are now experts in writing Lagrangian. So, the Lagrangian here will be something like this, the extra term that you get here, which is coming from z dot square. Okay. Now, we want to do that harmonic approximation. In the harmonic approximation, the amplitude is small. So, basically this r here, which is the distance, and theta both are small. Okay. Now, if r is very small compared to L, I can do a Taylor expansion of this, and if I do Taylor expansion, what I am left with is mg by 2L into r square. And similarly, if you look at this one here, r square is of course r square by L square is very small compared to 1. So, I will actually approximate this term out, and what remains of the harmonic approximation is half m r dot square by 2 plus r square theta dot square minus some constant into r square. But this is exactly like Hooke's law, which we studied in the central forces, and in central forces we used a theorem which told us that the motion there is actually elliptic. Okay. It is closed and bounded, and it is elliptic for Hooke's law. This exactly looks like Hooke's law there. But then when we actually draw the pattern looks like this. So, this is the photograph we took in our laboratory. Now, what is happening here is in fact nice study. As the pendulum moves, because of the friction at the support point and also some friction in the air, the amplitude keeps on decreasing. Okay. So, as amplitude decreases, you can see that the swing is becoming smaller and smaller, but then as time passes, you can see that this pendulum is settling down to elliptic orbit. Okay. And that is when this approximation will start becoming valid. But wait, again, if you observe it for long enough, very closely, that ellipse is slowly turning, okay, it's slowly precessing. This happens because of the small nonlinear effects which we have not considered, but they will be present, and if they will start showing after some time. So, again the takeaway from all this is, when we talk about small oscillations, we are talking about the problem becomes similar to a harmonic motion problem, but wait, at the same time we also understand that the motion that we observe should be observed for a limited amount of time. Beyond that, you will start seeing the effects of the non-linearity there. Okay. When I say non-linearity, basically what I mean is, if you look at the equation of motion, which is dp by dt is equal to f, but f is a linear force, it is minus some constant times x in, if you take a one dimensional case. So, we had non-linear forces which linearized to some sort of a minus kx type force. Okay. So, this is the introduction to what I mean by small forces, small oscillations. Now, let us look at this problem more carefully. Let me start by looking at a system which has n degrees of freedom, and as usual we will use the generalized coordinates q1 to q1. Okay. Now, the assumptions that we are going to make are the following. The first of all, the potential energy should be function of the generalized coordinates only. What I mean is, I am excluding the forces or potentials which depend on velocities and time. Secondly, the constraint forces themselves should be time independent, and finally, the transformations, remember when we write down the Lagrangian mechanics, we start with Cartesian coordinates and then make a transformation to generalized coordinates. These transformations, they are also independent of time. So, that is the assumption we will make. It is not a very restrictive assumption. It actually covers very large number of problems that we know in physics. In fact, many perturbation problems would fall in this category. Now, when we have a system and we look at potential, we get a equilibrium point. When do we have equilibrium? Equilibrium is when the generalized forces are 0, and generalized forces are defined as the partial derivative of the potential with respect to individual qi, and this generalized force for each I must be 0 at some point q 0, and then we say we have a equilibrium at q 0. But when you have a equilibrium at q 0, I can always make a Taylor expansion of the potential about the equilibrium point, and when I make a Taylor expansion, V q will be equal to potential at q 0 plus the first derivative of potential, but first derivative of potential at q 0 are already 0. So, I will drop that term from here and write the second partial derivative term here, and in this one basically a Vij are second derivative of potential with respect to Qi and Qj, okay, evaluated at q 0. So, basically they evaluate to a number, remember, and this eta which I have written here is basically a deviation from q 0. So, eta j is Qj minus Qj 0, and if you look at this one, I can put this Vij in a matrix form, and that matrix is called as Hessian matrix, okay. And how do I know that this is a minimum and not a saddle point like that one? That we already know from our discussion in the first few weeks, that if I go away from the equilibrium point, the potential must increase if it has to be a true minimum, okay, and that is when we get this what is called as a stable equilibrium. And what does that condition mean? That means if you take a vector in any direction, then the change in the potential energy, which is basically this term, must be greater than 0, okay. And this, when this happens for any eta, you say the matrix is positive definite, okay. So, what we basically want is Vij or V matrix must be positive definite for a stable equilibrium. Now, look at what happens to the kinetic energy part. The kinetic energy part, the same. Now, I will remind you something that we did in our first week. Suppose the transformations from Cartesian coordinates to generalized coordinates do not depend on time, then the kinetic energy term is basically homogeneous polynomial of degree 2, okay. There are only degree 2 terms there, which are basically products of Qi and Qj, or Qi dot and Qj dot, but the coefficient there of Qi dot and Qj dot, that may not be a constant, that may depend on Q itself, okay. So, what I am going to do is basically I am going to approximate this also to something like Tij into eta ij dot and eta j, eta I dot and eta j dot, okay. And because these velocities, so look at this, this is already second ordered in eta. So, I do not want any more eta appearing in this Tij. So, what I will do is Tij is constructed from these coefficients here, and which I will call as mass in some sense. These coefficients here, by just evaluating these coefficients at q 0, because Qi dot Qj dot already represents the second order term there. Okay. To give you an example of what I mean here is, look at this double pendulum. I will do the detailed calculation in next lecture or lecture after that. But right now I will just show you the kinetic energy term, and this problem also we have done in one of the earlier weeks. The Lagrangian or just the kinetic energy term comes out to be, so there is a phi 1 dot square, which is basically this angle, and phi 2 is the second angle. And look at this, this has a constant coefficients, but phi 1 dot phi 2 dot, the coefficient there, which is cos phi 1 minus cos phi 1 minus phi 2, that depends on phi 1 and phi 2. And what we are going to do is, because it already has been multiplied by this dot product, I am simply going to evaluate this coefficient at the equilibrium point. And where is the equilibrium of this double pendulum? Equilibrium of this double pendulum is at phi 1 is equal to 0 and phi 2 is equal to 0. So, basically that when I put that there, it will be cos of 0, which is 1, and that gives me a constant into phi 1 dot square, a constant into phi 2 dot square, and then there is a common term there, multiplication cross term there. Now, out of this cross term, when I construct this matrix Tij, what I am going to do is I am going to split this as phi 1 dot phi 2 dot plus phi 2 dot phi 1 dot divide by 2. Okay. So, basically this phi 1 dot phi 2 dot is same as phi 2 dot phi 1 dot, but when I put it in the matrix, I will divide this term into two parts, put one on the upper side of the matrix and one on the lower side of the matrix, and that way when I construct this Tij matrix, that will always be a symmetric matrix. Okay. So, this is how we will construct the kinetic energy term. So, the total Lagrangian now becomes, the kinetic energy term minus the potential energy term. Okay. And if you construct the equations of motion out of this, the equation of motion is basically, you take a derivative of this with respect to eta I dot, what you are left with is Tij eta j dot, and then you take one more derivative of that, that will give you one more time derivative of that, that will give you eta j double dot, and minus the derivative of v term with respect to eta I. So, that basically comes to a very straightforward linear equation, and in this one, remember this index I can go from 1 to n. That means, there are n equations in this, there are n independent equations in this. These are coupled differential equations, because Vij is not necessarily diagonal. So, the eta I dot and basically the differential equation for eta I will contain the terms from eta j and so on. So, basically these are coupled differential equations. Normally, we would like to put this in a matrix form. So, what I will do is I will put this eta in a matrix form. There are n components to eta, eta 1 to eta n, you put them in a column matrix and call it as bold symbol eta. V naturally fits into a square matrix, which is n by n. The kinetic energy also fits into a neat matrix form, and then if I write this Lagrangian, that would be half eta dot transposed T matrix eta dot and minus eta transpose V eta. So, it has a very neat matrix form, and the equations of motion after taking derivative, or you can just look at this equation here. This does look like a matrix equation, put it here in a matrix form. So, T eta double dot plus V eta, that must be equal to 0, and this is basically linear differential equation that we are going to focus on for the rest of the week. This is the approximation that we will come to for every problem where there is a stable equilibrium and a motion about the stable equilibrium. Okay. In the next class, I will take one example and explain how to solve this problem by using example first, and in the lecture after that we will try and find the general method of solving problems like this.